The title of my talk is a question, so I think I should allow people to ask questions during the talk. So feel free. Okay, so let's get started. So just to remind you, this is the collaboration, 17 PIs, and I think everyone is here. Also, affiliate Shuheng Shao, sorry, is also here. So this is the PI component of the collaboration. And of course, the community is much bigger. We've had more than 40 postdocs over the course of 7 years. Many students supported. Many of these postdocs have gone on to faculty positions now. I don't actually have the entire list. Certainly don't have all the photographs. And in fact, Shuheng is now part of the collaboration as an affiliate. Okay, so this has been, I think, the most rewarding component, one of the most rewarding components in terms of launching all of these young people. Okay, so when you have a question like this, what do you do, right? So even 3 years back, when I had to give this renewal talk, even at that stage, we asked ChatGPT. So let's do the same thing over here. Let me actually compare what answer we got then compared to what we have now to see if there's been progress, if at least the LLMs have learned, right? This is the old answer, yeah. This is the 2003 answer. And you see, it's okay. It's some things are kind of off. State of matter, not quite. It's characterized by strong quantum correlations. That may be okay. Include phenomena such as quantum coherence. That seems a little bit off. That's kind of a given. I'll try. Yeah. So it's not too bad. But what I can say is that it's certainly, if one thing has improved and one thing has learned, it's this. I think this is a much, much better definition and pretty close to what I would have said. It's irreducibly quantum, robust non-local entanglement, different from independent particles. It's motivated by systems like the quantum Hall effect, spin liquids, topological phases, unconventional gapless metals where entanglement and emergent gauge structure are central. Okay, so that I think is a pretty good definition if you want to have a laundry list of topics that all of us have been interested in, the kind of unifying themes that all of us have been thinking about. Okay, but actually personally, when I was thinking about this question, I'd maybe answer it a little differently. And I think basically what the collaboration has actually been a methodology, sort of philosophy for theory building. And there's sort of a few components in that. So one would be to really emphasize conceptual ideas, okay, conceptual points, organizing principles, rather than jumping into a calculation and things that would be more typical in many subfields. Okay, so some of the things we have learned over the past few years is that symmetry and topology place very strong constraints. There are relations between the two, and we are still discovering some of these constraints and how to make them work for us. Okay, anomalies and the constraints they place on quantum systems. This is sort of the first order of business when you think about a new quantum many-body problem. But at the same time, we don't want to end there. We don't want to stop with that. We'd like to eventually connect all of these ideas to actual microscopic models, well-defined microscopic models, and hopefully also to experimental reality. And even if one person in the collaboration cannot do all of this, as a collective whole, we can seek to span this entire space, and then the interplay between different people and students and postdocs talking to one another, coming from these slightly different motivations, as a coherent whole, sort of realizes these principles. Okay, so that's sort of words, but I'll try to illustrate this during the course of my talk with a few examples of things that came out of the collaboration, which illustrates these different points, maybe emphasizing some rather than others, depending on which example I'm talking about. I'll first talk about a set of examples that is not very well represented at this meeting. So I give a little bit of spotlight to that, and then I'll talk about some of my own group's research work. Okay, and the way in which we have sort of tried to implement this philosophy, really, to guide the collaboration, has been through the meetings. So this is sort of the last meeting, one of the last meetings we had, last few meetings we had at Chicago. A lot of discussion, and we don't always have a blackboard that looks like that, but that was a particularly good example. So we've had more than 19 meetings over the course of 7 years. It's actually a little bit less than what we would have expected, given that part of the collaboration overlapped with the pandemic. But we kind of made use of that as well. We had some of these virtual summer schools and programs that had many, many people attending. Our typical numbers of people attending the meeting, some of the bigger meetings have been 120 plus. We've also had mini meetings where it's about half that size. And I think over the course of these meetings, cumulatively, there's been a lot of sharing of ideas, and groups of people who don't otherwise talk together have gotten together, and it's actually been very fruitful. Okay, so I'll try to give some examples of this kind of cross-pollination as we go along. And so this is sort of the outline for the rest of my talk. I'll have 3 different highlights. And one of them will be about UQM approaches to the theory of metals. So that's not very well represented in the talk, so I'll sort of cover some of the highlights. And then I'll talk about what UQM can do, what it can provide, in terms of maybe realizing new materials properties enabled by these highly entangled quantum states. Can we actually do that? And then perhaps using these for other things that we are interested in, quantum error correction in particular. But let me start with these gapless UQMs applied especially to the theory of metals. Okay, so this is where we've had quite a lot of success, I would say. Here are a few of the highlights. I won't spend too long on them, but just highlight how I think they illustrate these aspects of UQM. So there's a very nice paper by Senthil and collaborators, series of papers actually, there's just one over here, where this whole idea of symmetries, also in its generalized form, higher form symmetries, and anomalies, the anomalies accompanying these, was applied to think about resistivity. Okay, so resistivity of metals or superfluids, superconductors, and so on, and use these kind of strong non-perturbative constraints to constrain theories of non-Fermi liquids. Okay, and that I think was sort of an example of these constraints and modern ideas in theoretical physics influencing a very old problem, the theory of metals. Okay, similarly, there was a very nice work by Damson and collaborators where they introduced a completely new way to think about the Fermi surface, a really left field way of approaching this problem, which is called the method of coadjoint orbits. Okay, so I'd encourage you to talk to these people to learn more. And then the third highlight in this subfield is by Subir and Yahui Zhang, where they came up with a new approach to write down wave functions for an exotic state of matter, the so-called FL star state. So this is a state that's been known for a long time, but it's been really hard to write down wave functions that live in the physical Hilbert space. Okay, it's a coexistence of fractionalization and Fermi liquid, but they came up with a new construction called the ancilla construction, which allows them to make progress in this direction. Okay, and the interesting thing about this ancilla construction, I won't actually go into the details, but it has these 3 different layers. There's a layer where the conduction electrons live, if you like, and then there are these two other ancilla layers. And the idea basically is to put one of the layers in a spin liquid in the exotic state that you want, and then effectively use quantum teleportation. So the quantum teleportation protocol, where you have a EPR pair, and then you project or you go and measure one member of the EPR pair and the qubit of your choice, you use that information to teleport the wave function from the bottom layer to the top. Okay, so this is kind of the idea in this ancilla theory. It's been extremely useful for other problems as well. And we'll see in a few slides, there'll be another application of this kind of quantum teleportation, but to a completely different problem, to the problem of creating novel quantum states. So this is another example of some convergence, ideas maybe from quantum information or from quantum computing being useful here in solving an old problem. Okay, and this particular state is a candidate state for the so-called pseudogap phase of the cuprates. Okay, so it has major implications, not just here, also been applied to other settings like twisted bilayer. Okay, so that was the three topics I wanted to mention in the context of these gapless UQAP. Okay, so now let me kind of switch and talk a little bit about creating new materials properties because you're coming from these quantum states that are highly entangled or exotic in some way. Okay, so as condensed matter physicists or solid state physicists, we have a sort of folklore about what to expect, what can happen, and so on in metals or in conventional systems. But all of these are predicated on a certain conventional sort of viewpoint, right? And if you change those rules, you could have an advantage. You could come up with things that look unusual and sort of beat what people have taken for granted in the past. Okay, so so this has sort of three subparts. I'll begin by talking about quantum phase transitions of a particular kind. So it'll be a phase transition from one insulator to another. But then we'll think about doping these insulators. Okay, and near the critical point, I'll argue that we expect superconductivity for a particular family of these insulators. And this will really be a different mechanism, if you like, of getting superconductivity. So superconductors themselves, in some ways, are conventional. You think of them as a condensation of Cooper pairs. But the big mystery for solid-state physics is why do electrons with repulsive interactions decide to form Cooper pairs and condense? Okay, so it's really somewhat of an energetic problem rather than a problem about describing the final state. Okay, so you want to think about new mechanisms which enable that. And in these kind of discussions, it's very important to follow the rules of having electrons with repulsive interactions. Okay, otherwise, it's completely trivial to get superconductivity. Okay, so we'll try to build that into this discussion. Also talk about a somewhat related topic, which is superconductivity from a finite density of anyons. That'll be the ultra quantum matter, having non-trivial quasi-particles with fractional statistics could give a different mechanism for superconductivity. And finally, I'll talk a little bit about something new that we are excited about, topological superconductors, but now with charge 4e. Okay, something I've been trying to look for a long time. And it turns out with one extra ingredient, you can actually create new kinds of topological superconductors once you admit pairing with charge 4e. Okay, so let me start with these quantum phase transitions between pairs of insulators. So these are both going to be insulators. So there's you tune a parameter, go from insulator 1 to 2. They're going to differ at the level of topology. Okay, and we're thinking of the phase transition over there described by some conformal field theory. It does not have to be. That'll be the simplest setting. It could be a more complicated critical theory. You could also not have a continuous transition, but something that is weakly first order. A lot of the things I'll say will go over. But this is the absolute simplest setup where we have a conformal field theory describing the critical point between a pair of these insulators. Yeah, and for certain pairs, for certain choices of these pairs, it'll turn out that when you dope the system, so you add some doping delta, add electric charge, it's quite natural to end up in a superconducting state. Okay, so which kinds of insulators am I thinking about? So I'll give two examples. Both of them will involve fractionalization will involve topological order. The first will be a transition between a very conventional integer quantum Hall state, that will be, say, insulator 2. And on the other side, we'll have a spin liquid, so that's an exotic state, chiral spin liquid. And it's possible to have a transition, and we'll ask what happens near that critical point. Okay, now, of course, these are, both of these are theoretically easy to describe, but we don't have examples of chiral spin liquids. What we do have examples of fractionalized states are fractional quantum Hall states. Okay, so the question is, can you perhaps change this into a fractional quantum Hall state? And in fact, I'll talk a little bit about a model where you can have one of the insulators being a fractional quantum Hall state. The other will be a different insulator where we have this transition. And then again, interesting things happen when you try to dope it. Okay, so let me begin with the first one. So we're thinking about doping. Mu is the chemical potential. And let's say you start in insulator 1 and add electric charge or change the chemical potential. Now you have a finite density of electrons. Where do we go? Okay, so if indeed you start with a chiral spin liquid and you have this scenario, you would have realized something that people have been looking for a long time, superconductivity emerging from a spin liquid. Okay, and the real question is, do you have microscopic models? There are many well-motivated theoretical ideas for this to happen, but can you actually implement that in a microscopic model? Okay, the second option, which is we start with the fractional quantum Hall state. That will be the second thing I'll get to. We'll think about doping the fractional quantum Hall state in the vicinity of this critical point. Critical point will help us organize various energy scales. And what we would expect if you had such a transition is that you begin at 0 doping with in the 2/3 fractional quantum Hall state. So the Hall conductance is quantized to 2/3. Hall resistivity is quantized to 3/2, the inverse of that. And then when you dope it, this resistivity along with the rho XX, the longitudinal resistivity, should simply drop to 0. Okay, that's the kind of electrical signature you're looking for, and again, the question of microscopic models. Okay, now this thing may remind you of some recent experiments where people took a material called molybdenum ditelluride with a twist in those materials at the right electron filling. As you vary the electron filling, you can get integer quantum Hall states and fractional quantum Hall states, like, for example, the 2/3 state. And you can do this all in the absence of a magnetic field. Okay, in fact, the effective magnetic field in this material comes from the length scale set up by the twist. It's actually very large. It's like 100, 150 Tesla. Okay, but you can do it all in 0 magnetic field. This has been a major discovery in the condensed matter field. And in this follow-up work, what they found is that going to maybe cleaner samples, if you add electric charge to this 2/3 state and you go to a slightly different filling, they saw the resistivity dropping by quite a bit, and they identified this with the superconductor. Okay, so this may remind you of what is happening over here. There may be other reasons to get a superconductor, but it would be very nice to see this in actual models. Again, there's been many other people working on this problem. There's a separate model by Tiger and Mike Zalatel, and we'll hear a lot more about all of this in the talk by Senthil. Okay, so let me sort of elaborate a little bit on the first point, which was getting a superconductor from a chiral spin liquid. So the model we have in mind is extremely simple. It's just a Hubbard model on the triangular lattice with one twist, literally, which is we put in a magnetic flux through the plaquettes of this Hubbard model. Okay, so there's a magnetic flux of pi/2 in a triangle pi inside a unit cell. So effectively, you've doubled the unit cell because you need to have 2 pi flux inside the unit cell. Okay, so this is a triangular lattice Hubbard model where, because of flux, you have doubled the unit cell. Okay, now of course, if this was at the atomic scale, this is hard to believe you can apply a magnetic field of that size. But now we have lattices at the Moiré scale, which is a factor of 100 bigger. So you can achieve these things with reasonable magnetic field. The tricky part will be, how do you actually have a model like this, which includes spin without a Zeeman field? Okay, we have ideas for that. where the spin is not actual spin, but some kind of pseudo spin. But for now, let's just take this model. It's quasi-realistic. It could be realized with some work. You have a Hubbard model with some hopping. Hopping involves the phase factors coming from the flux, and only one term for the interaction, which is an on-site repulsion. Okay, so what is the phase diagram of this model? Of course, it depends on the filling, but let's say we have filling of 1 electron per site. Okay, so from the usual band structure, if you had no flux, you had 1 electron per site on the triangular lattice, you'd get a metal. Okay, you have just one site in the unit cell. But in this case, because of the flux, you've doubled your unit cell, you can get an insulator. You can get a band insulator. In fact, you do. So in the weak coupling limit, you just have Chern bands, which you fill. It has Chern number 1, and you get a total Hall conductance of 2 times the quantum of Hall conductance, 2 because of the spin up and spin down. Okay, you can also define a different response, which is instead of applying electric field and measuring current, you can apply a varying Zeeman field. Imagine the Zeeman field varies. And then you go and measure the spin current. Okay, so the spin quantum Hall, and that is also has strength 2 in the appropriate units. Okay, this is just an integer quantum Hall insulator with both spin up and spin down. Okay, now the interesting question is what happens as I crank up repulsion. And this was discovered by Clemens, who is here, and his collaborators, that as you go beyond a critical interaction strength, you transition, as you must, because now your U is becoming very important, and you have 1 electron per site. Okay, so you should actually treat the U as the first term in your Hamiltonian, or at least that they are of equal strength. Okay, and what is found is that you get an insulator, so it's a transition from one insulator to another, but this insulator has no interesting electrical charge properties. Okay, the Hall conductance is 0. And you can see this in numerics, in the DMRG numerics, simply by threading a magnetic flux and seeing if there's a Laughlin charge pumping. There is charge pumping on this side, but not over here. There's no charge pumped as a function of flux. Okay, but it retains the spin Hall conductance. So the spin Hall conductance remains 2, and these are precisely the characteristics of a chiral spin liquid. It's got a chiral edge mode. It's got fractionalization because having this pair of Hall conductances is not compatible with a non-interacting electron description. Okay, so it's really a fractionalized state. It has topological order, U1 level 2. And the question is, how do you go from this insulator to that? Does something interesting happen on the way? Okay, so that is really the question we want to think about. You change U. You go from integer to chiral spin liquid, integer quantum Hall to chiral spin liquid, and already you can make a few statements. One thing you can say is that the charge gap has to close. So if there's a gap to charged excitations, it's got to close and reopen. It's got to be finite on either side because they're insulators. But it's got to close and reopen because you have to change the Hall conductance. Okay, but on the other hand, the spin Hall conductance has stayed the same. So there's no reason a priori for that to close. It could remain open throughout. In fact, that's what we're going to see that happens. So now you see that you have a situation where you have very low energy charge excitations here, but there's a spin gap. Okay, so this is kind of the ideal setting, at least for Cooper pairing. So if you add electrons into the system, add charge, it's unlikely to go in as electrons where you have to pay the spin gap price. It's much more likely to go in as Cooper pairs where you can add charge for very little energy, but you don't pay any cost. Spin singlet Cooper pairs where you don't pay any cost because of the spin gap. Okay, so you can ask, is there a field theory that will allow me to connect these two sides? Just zooming out and thinking about the long distance physics. And it's very easy to construct such a field theory. You can do a more microscopic calculation where you can even get the critical point, or at least an estimate of the critical point. But let me take a more field theory approach. I have some bosonic field psi, and if it is minimally coupled to a fluctuating gauge field little a. If this field is condensed, as it is in this G less than 0, then this little a is quenched, it's Higgsed, and I simply get the topological response for an integer quantum Hall state. Okay, there are some other terms I've omitted over there. You can use that to get the chiral central charge and so on. On the other hand, if it's gapped, I can simply integrate out little a, sorry, if it is gapped, the little a dynamics is present. I cannot integrate it because it has a non-trivial level, but I can absorb the capital A into little a. So you have no electrical response, but you have topological order, U1 level 2, and that's the level over here. So that is the chiral spin liquid. Okay, so the simple theory, just it looks like an abelian Higgs model. It has the additional feature that there's a Chern-Simons term. Okay, and this is able to describe essential physics of either side of this transition. Okay, so this theory has many duals. Some of these dual descriptions are better than others in the sense that actually our microscopic model, it turns out, has an SU2 symmetry. It has what's called SU2 pseudospin symmetry. It's more than the U1 that this naturally admits. Some of those other descriptions can explicitly accommodate that SU2 symmetry. But there are, the duality suggests that this will also have emergent SU2. So this was something pointed out by Natty and Potions a few years back. And so this is describing this transition where the spin gap remains open and it's just the charge physics that is being modified. Okay, so there's another problem that you can relate this to, and this is where, yeah. No, there's just one, yeah. So this has to do with the fact there's flux in the lattice. So the electron transforms, has a magnetic translation symmetry. So it turns out if you think of partons, B times F, the boson B has trivial translation symmetry. Unlike, say, the usual triangular lattice, where you may be kind of relating to that problem. There, the slave boson actually has non-trivial magnetic translations. Yeah, so extremely simple theory. A single valley, there's a single low energy mode, comes down and condenses. That's the transition. Okay. So another thing you could relate this problem to, interestingly, is we are, as far as phase transitions go, you're allowed to add invertible phases, things like integer quantum Hall phases. So you can add the inverse of this particular phase, the inverse of the integer quantum Hall phase. So integer quantum Hall sigma xy minus 2. You slap that on to the system, this becomes just a trivial insulator. It's got no Hall response. And then you can ask, what is this state over here? It now has a Hall response of minus 2, electrical Hall response of minus 2, but no spin Hall response. Okay, so you've quenched the spin physics, and the charge physics has become active. Okay, so basically it tells you that this theory can also describe the transition between a trivial insulator and a Laughlin 1/2 state. Okay, strictly speaking, I should say minus 1/2. You'll have the same topological order as this chiral spin liquid. You'll have semi-on fractionalized excitations, but you can now think of it as the bosonic Laughlin state. The bosons in this particular case are actually Cooper pairs. So Cooper pairs, yeah. In this, I didn't put it in, but there is, yeah. There's a background which doesn't change at all. So you can introduce a gauge field to probe the spin, AS, and it has like 2 times AS DAS. Yeah, and they're the same, yeah. Okay, so this is a different transition you may be interested in. Confinement of the Laughlin 1/2 state, the simplest confinement transition of fractional quantum Hall. It's the same as this critical point. Okay, and recently there's been very nice numerical evidence from Yin Chen and Zheng Zhu and Chong Wang that using these fuzzy sphere numerics, they found a way to put this on the sphere and look at the, in fact, in this form, and look at the scaling dimensions of the operators, the entire conformal spectrum, and they make a strong case that this is a continuous phase transition. It's just got one relevant operator. Okay, so this is one of the cases where it's simple and everything seems to be in good shape in terms of guaranteeing at least the possibility of a CFT transition. Okay, so now let's go to finite doping. So one of the interests for us in thinking of these transitions is that we get new kinds of physics when we add charge to this problem. And another reason we may want to think about doping a critical point is the following. Usually, if you think about an insulator and you dope electric charge, you send in a density of charge delta. You think of these as forming some kind of band. They have some effective mass. And it's what you would expect is that the superfluid density goes as the number of particles you put in. Okay, so superfluid density will be proportional to the density of charge. Rho s goes as delta. That is the usual expectation. Okay, but there's a very simple scaling argument that if you get a superconductor on doping a CFT, the only length scale that you have at that point is the separation between the doped charge. Okay, and so that length scale is, one over the length scale is square root of delta. And at the CFT, you have a universal velocity in the speed of light, speed of sound. And so you can combine that to get an energy scale, and that is the unique energy scale in the vicinity of a critical point with z equal to 1. So then you expect the superfluid density to scale as square root of the doped charge. Okay, so at least for very small charge, this is much bigger than the conventional doping, the conventional scaling. Okay, so there is a qualitative reason why you might think that superconductivity is robust, at least at weak doping in the vicinity of such an insulator to insulator transition. Okay, so now let's think about finite doping. And there are two stories you need to come up with. What if you dope on the integer quantum Hall side, and what if you dope on the chiral spin liquid side? Okay, so on the integer quantum Hall side, it's very simple. You have as you approach this point, you have low energy charge excitations. They're all unfractionalized. They're just electrons, Cooper pairs, things like that. But there's a spin gap that is finite. So the lowest energy, the cheapest charge excitation is Cooper pairs. You put in a finite density of Cooper pairs, and you get a superconductor. Okay. The argument on the chiral spin liquid side here is more involved, because now you can make charge excitations that are spin singlets that are not Cooper pairs. Okay, these are really the fractionalized excitations of this state. You can think of it as a spin-on of the chiral spin liquid carries spin a half bound to an electron. Okay, so together they have no spin. They don't pay the spin gap, but they carry charge. Okay, so those are the objects you're going to dope in as you approach the critical point. Okay, now the question is, if I give you a finite density of those particles, they're semions, they are fractional statistics, they have electric charge, what is the fate of that gas of particles? And so there are different ways of arguing this. So this is a problem that goes back to Bob Laughlin, where he made this inspired guess or he had good reason for it, as an educated guess, that this collective state would be a superconductor. Okay, and from the field theory point of view, essentially what happens, you write down the effective field theory for the chiral spin liquid, and then the doped charge will give you an additional term. Okay, so you get additional terms on doping with the anyons. Let's see what they are. Let me just write it down. You end up getting this additional term. And if you put them all together, you get this effective action. Okay. So if you stare at this action, little a is a dynamical field. So basically, if I transfer the derivative onto capital A, little a acts like a Lagrange multiplier. It forces the fluxes of capital A, the external magnetic field, to be 0. Okay, so that is really just the Meissner effect. This is really a superconductor you're talking about. It's at an extreme limit where I've dropped the Maxwell term. If you add the Maxwell term for little a, you will also get a finite penetration depth. This is kind of the field theory limit where you've taken the penetration depth to 0. Okay, and then you have this background topological term. In terms of response, this doesn't really do anything because it's subdominant compared to the Meissner term. But what it's actually telling you, if you were to gauge this capital A to figure out what kind of superconductor you have at the end of the day, is it an S-wave superconductor with no edge states, or is it something more interesting? If you were to gauge capital A and look up Kitaev's table classification of topologically ordered phases, you'll find that this is really a D plus ID topological superconductor. So D plus ID in quotes because it's not really the literal form of the pairing symmetry. It's the fact that it has a chiral central charge of 2 units in the same direction as the Hall conductance. Okay, so I'll call that D plus ID, although you have to be a little bit careful in actually specifying what that means. Okay, so this tells you that this superconductor over here, in fact, you get the same result if you go from this side or that side. You could have a single, single phase of superconductor. It's a conventional superconductor in the sense that it has no fractionalization, no exotic particles. It's unconventional in the sense it has edge states, but that's kind of a mild version of unconventional in this context. But it's obtained by an unconventional mechanism, by doping these anions and getting into the superconductor. Yeah, yeah. From this integer quantum Hall side? Yeah. So we know the chiral central charge of integer quantum Hall is C equal to 2. Now imagine just condensing Cooper pairs on top of that. You lose the charge response, but you have, yeah. Yeah, that yeah. Yeah, you're right. Everything is in this term over here. So, yeah, yeah. So what you do is you think of changing the density of particles, but what you want to do is you want to maintain the spin gap. So if you think of a parton construction for this, say, B times F, you're going to adjust the flux that F sees so that it accommodates a slightly smaller number of particles. So F is in a Chern band. So you adjust the internal flux when you dope it to keep it in an insulator. And this additional flux is seen by these bosons. So doping does two things for the bosons. You change the density and you change the flux that they see. And if you look at the commensuration between the two, it's as though the bosons are at filling 2. Actually, they're at filling -2. Yes, independent of the density, because they go in tandem. The flux that you see and the density goes in tandem, which is what it should be for a compressible phase. And then the most natural state, this is actually, you need dynamics to actually say this, but a very natural state is to say you realize what's called a bosonic integer quantum Hall, which is exactly at that filling fraction. If you assume that, you get precisely this response. This is the Hall response of bosons in a bosonic integer quantum Hall phase. The Hall conductance is 2 units in an opposite sign. So taken together, that kills off the topological order, and you get this. So this is a very general mechanism for all of these things that people call anion superconductivity.
Yeah. So if you did this for the version where you go from the trivial insulator to the 1/2,
yeah,
that you'd also have anion superconductivity.
Yeah.
It would be S way instead of B plus ID. It wouldn't have the edge state.
Yes, yes, I think that's right. Yeah, yeah, that's right. Yeah. So it's actually nu equal to -12 Laughlin. It gets flipped. Yeah, and you're right. The other one does not. So yeah, it'll be like S wave, no edge states. But yeah. So yeah. So it's the distinction between having topological order and topological insulators. It's invertible, it has edge states. Yeah. Yeah, and I should have mentioned a lot of people here have worked on this in the past, anion superconductivity under that name, and it's kind of had a revival in recent years. Okay, so now, so that was the integer filling. Everything is nice, but of course, we're stuck with this chiral spin liquid. Question is, can you do something at fractional filling? Okay, and this actually came as a big surprise to me. So these young collaborators of mine, Hannes and Clemens, Hannes is a student of Michael Knapp. So they decided to play around with a variant of this model, which I would not have suggested them to do, but I'm glad they did. So they looked at filling 1/3. Okay, so instead of filling 1, they look at filling 1/3. And then you have to do a few more things to the model, not major things. One is you want to make the band flat. Okay, now you have fractional filling, you'll usually get a metal, but not if you flatten the band. So they played around with the second neighbor hopping T prime, adjusted to get a flat band. And then because you have very low density of electrons, you need to have some additional repulsion to make life interesting. So nearest neighbor repulsion, not just on-site nearest neighbor. Okay, so that's the model, a small variant at filling 1/3. Okay, and now what they saw is that if you look at this phase diagram as a function of u over t and this interaction v, the neighboring interaction, Amazingly, you find this phase, which is fractionally filled churn band, which gives you the fractional quantum Hall effect, okay, the fractional churn insulator, if you like. Okay, so this is what you'd expect if you fill a churn band with filling two-third because you have two sides in the unit cell, so you double this over here. Okay, but what's even more interesting is that when you increase interactions or change interactions, you get two other phases. One of them is a conventional charge density wave. Electrons go and form a crystal on every third lattice site. They also have spin, so that spin ends up ordering. Okay, but there's a third phase, which is very unusual, where you form, again, a charge density wave on a bigger lattice, but that charge density wave has semi-on topological order. Okay, so it's like instead of having an ordered pattern of these spins, the spins disorder into a chiral spin liquid over here, okay, to the extent that you can think of it like that. So this is a very surprising phase. So it was one of the phases that Senthil and collaborators found when they were thinking about instabilities of a two-third phase. But in the absence of spin, it's very hard to imagine how you get this phase. Yeah. So it's just chiral spin liquid. So if you didn't worry about translation symmetry, it's just chiral spin liquid. Okay, so the fact this model has spin makes it, makes this a more believable kind of ground state. Okay, so let's look at this phase transition. When you crank up the interaction V as a function as you go from this phase to the next. Okay, so this is kind of the phase diagram that you would expect. So at small values of V, you get the fractional churn insulator, and it's essentially a two-third filling state with spin, the very natural state called the Hall-Print state. Okay, and in terms of topological order, it's the same as the usual two-third state. It has anyons that carry fractional statistics of two-third, but it's nice to enrich it with spin rotation symmetry, which is what happens in this model. And what you can see, it has, the charge response is two-thirds of the quantum of conductance, and the spin response is -2. The spin response in a model with SU2 symmetry has to be multiples of 2, whether it's fractionalized or not. So this spin response is -2. Okay, so this is the Hall-Print state for this two-third. And then if you crank up the interactions V, you end up getting this CDW. Numerically, it's found that you end up getting the CDW, which has no electrical Hall response, but it has the same spin response as the other phase. So it's very much like our previous example. Spin response goes right through, but the charge response changes, and you end up getting this, this insulator. Okay, so one way to rationalize this, once you know the answer, you want to understand how on earth did you get this particular phase. One way to rationalize it is you can look at this bigger triangle over here. This is the triangle formed by electrons in the charge density wave. It's 3 times the size of the original triangle. Okay, so it kind of looks like the original lattice. The original lattice had pi/2 flux. This will have 3 pi/2 flux. Okay, so maybe you could again get a chiral spin liquid. Okay, but what you'd predict is that if you do get a chiral spin liquid, it'll have the opposite sense, 3 pi/2, so it's like -pi/2. In fact, that's what happens. You get chiral spin liquid rotating in the opposite direction. Okay, so that's the rough intuition. Of course, you're not so deep into the phase that this charge density is that strongly a charge density wave, but somehow it works out. Okay, so again, similar phase diagram. The spin is gapped. The charge should charge gap should close and reopen if you have a continuous transition. Okay, and you can write down a field theory for this. So this is very similar to field theories that Subir and Leon wrote down with multiple vortex species. So now you get multiple valleys for these vortices. They can either be gapped or they can condense, and they end up giving you these 2 different phases. Okay, all the complexity is living in this Chern-Simons terms with various gauge fields. Okay, so and in this particular case, the superconductor you get is D minus ID, and you can again, argue that on the 2/3 side by finite density of these 2/3 charged anyons. Okay, and it's important that they are 2/3 charged. The dynamics of this model automatically singles out these as the lowest energy anyons. Usually, if you had a 2/3 state in fractional quantum Hall, you would have got the E/3 anyon. That was low energy. You wouldn't get this particular type of phase diagram. Okay, but by having the two-thirds state in proximity to this chiral spin liquid plus CDW lowers the energy of this two-third anion, not the minimally charged anion. It's a spin singlet. That's why it's preferred. And then if you dope that in, you end up getting, you expect to get superconductivity by very similar arguments. Okay, now we don't quite have the finite doping numerics in this case. We do for the other one, and Donna Sheng and Leon also had a paper on that. But we can sit in the insulator and we can look at signatures of whether the gap states are like Cooper pairs or they're like single electrons. Okay, and you do see that the correlation length for spin is exponentially decaying, or it's fairly short range correlated, giving you evidence for this kind of scenario that doping this will end up going into the superconductor. Okay, so let me say one more thing. Switch to a related topic. This one we don't quite have a model, but I still think the phenomenology is quite interesting. So this is really trying to come up with a superconductor which is now not built of charge 2e Cooper pairs, but charge 4, so Cooper quartets maybe. And this is something that's in preparation. So we saw that this two-third fractional quantum Hall state could go into this d minus ID superconductor. That was the story I told you just before. That transition, if you happen at fixed density, is what's, it can be described by a QED3 transition. There's a more exotic variant. There's a different state that you could go into if you enrich the Maxwell electrodynamics to quantum chromodynamics, so QCD, SU2 gauge fields rather than U1. Why you should do this, it's not clear, but let me take that point of view. And then this leads to a different superconductor. Okay? And this superconductor turns out to have this Cooper quadruplet, so charge 4 superconductor, Cooper quartet. But it actually has some additional stuff there. It has some additional topological order. Okay, so the additional topological order is what we might call Z3. It's a chiral topological order in the sense that it has these 3 anions. They have some non-trivial topological spin. And these have the same statistics as the excitations, same fraction statistics as the excitations in two-third quantum Hall state. So in a way, the anion content is not changed, just from the anion point of view, but the symmetry properties are very different between this and that. Okay, so first of all, you've broken the full U1 down to this charge 4e. So the U1 has been broken down to a Z4, if you like, if you live in the broken symmetry state. And then you can ask, how does the Z4 act on these anions? Okay, so how does the symmetry enrichment act? And this is where it's very interesting. If you take a vortex, H over 4e vortex, in this charge 4 superconductor, and let's say you have one of these anions A over here, you take it around, this anion goes to A squared. Okay, so it's a symmetry enrichment where acting with this particular symmetry, the Z2 symmetry, taking the vortex around another particle is really like acting the Z2 symmetry on it, part of the unbroken Z2. It exchanges the anions. Okay, so this is, we have not seen this kind of superconductor before. If you think about comparing it to the more familiar case of Majoranas, there are 3 different ways in which people want to get Majoranas, right? You can get them in quantum wires, 1D, Kitaev chain. You could get them as dislocations in the toric code, twist defects, or you could get them as vortices in a P plus IP superconductor. Okay, for the Z3 version of this is something, this vortex would be like a Z3 parafermion. So something similar to this can be realized on the edge of a Laughlin state, 1/3 Laughlin state, by adding superconductivity to it. That's the 1D realization. There's 2D realizations called G-nons due to Mesam and Xiaoliang and collaborators. But this entry is kind of missing, right? How do you realize this kind of Z3 parafermions in a superfluid? Okay, and it turns out that you can do it in a charge 4 superfluid if you supplement that with some topological order. Again, this is the missing thing that is sitting there. Okay, so let me finally, in the last 10 minutes that I have, let me very quickly tell you about this third highlight, which is about trying to use quantum information tools. So we've seen a lot about using quantum information tools to help with quantum matter. understanding quantum matter. But let's ask instead whether quantum matter, what can quantum matter do for quantum information? Right? Can all the things we have learned about SPTs, gauging, topological order, symmetry enrichment, all these things that we have been kind of imbibing over the last few years, it should help us with some, it could help us come up with new ways of processing quantum information. Okay, and one very promising route is to use non-abelions to store and process quantum information. So in itself is not a very new idea. But now that we know so much more, maybe we have other ways of doing it. Okay, so I was going to go through this slide, but let me very quickly make the point that you can use measurements to create complex quantum states, not unlike the ancilla wave function discussion. You can go from a state that looks like this, that's not entangled, to a Bell state simply by making this joint measurement, measuring the product of spins, but don't measure the individual spins. Okay, so if you measure the product of spins, it turns out to be +1, you automatically collapse the state into the Bell state over here. Okay, so you can create entanglement with measurement if you have the right kind of measurement. Even if you get the result -1, you can act with a unitary operator and flip the spin and go back and create this particular Bell state. Okay, so regardless of the outcome of measurement, you can do some action based on the outcome to deterministically create a particular state. Okay, so we're going to use this idea, but in a more complex form to create complex many-body states. Okay, and you can kind of see what's happening over here. You're taking a pair of Ising spins and you're going and measuring if there's a domain wall between them. Okay, so there's some kind of duality. You're going to the dual variables. So basically what this approach allows you to do in its most general form, it allows you to take a state that is symmetric under a particular symmetry, combine it with ancillas. You go through this process of measuring and making modifications, and then out comes a state which is the gauged version of the symmetric state. Okay, so if you start with the disordered state of the Ising model, which is what I had before, all the spins along X, push it through this thing, you'll get to the ordered state of the Ising model, the Kramers-Vanier dual, and that's nothing but the GHZ state. Okay, so that's a simple example. You can do this in 2D. The disordered state of the Ising model becomes the toric code, and so on and so forth. Okay, so with Ruben, Nat, and Ryan, we figured out you can use this process to create certain non-abelian topological order, which can be got by sequentially gauging abelian groups. Okay, and those kind of groups are called solvable groups. So any topological order described by the quantum double of a solvable group, we can efficiently prepare. Okay, so there's kind of a hierarchy about topological orders, anyon models, very general, string nets. We are down here, quantum double of a group. Depending on what the group is, if the group is Z2, that's toric code. If the group is non-abelian, you get a non-abelian topological order. Okay, so we want to explore this alternative to the standard model of doing fault-tolerant quantum computing. So everyone right now who's trying to do fault-tolerant quantum computing, all the big companies are trying to do this. Take the toric code or the surface code, that's a good quantum memory. You can do certain gates by doing things called lattice surgery. And then you have to add something, it's called magic state distillation. Somewhat outside this topological framework, but still supposed to be good. You can add that in order to create a universal gate set, something that can create any unitary required in your computation. Okay, I'd like to think about a different alternative, which is you create non-abelian anyons. So in this vacuum, you create non-abelian anyons, use them to store the quantum information, and then use braiding, for example, or fusion of these non-abelian anyons to implement your quantum gate. Okay, now, of course, as people know, depending on the complexity of these anyons, you can either be universal or not. If it's Ising-like, you can only get Clifford gates, just like that. If it's Fibonacci, you can simply do braiding, nothing else, and you can execute all quantum operations in principle, but the gates look really complicated. Even doing simple gates needs many, many braids. It's also hard to prepare. It's not of this quantum double of a solvable group form. So we think the sweet spot is a group like S3, the quantum double of a group like S3. This is universal, not just with braiding, but you have to add fusion of anyons. Then together, so you add measurement to this braiding, it will be universal, but at the same time, it is easy to prepare. Okay, so this is the kind of thing we're trying to explore. And we've been doing this on this quantum processor, the trapped ion quantum processor. This was what we started out with at Quantinuum. Now they've upgraded it to, I think, 56 qubits. And they have very good 2-qubit fidelities, so that allows us to actually create these states and then add in anyons by acting with unitaries, for example, string operators that create anyons at their ends, and then doing these quantum gates. Okay, so previously we used this process to create the quantum double of D4. That unfortunately is not powerful enough to give you universal quantum computing. That's why we have recently upgraded to S3, so this should be coming out very soon. So this S3, it's been known for a while. You can make it universal if you have braiding and fusion. Okay, so what we'd like to do is to demonstrate the primitive gates that will make it universal. It's going to be on a small system, but the fact that you can execute all of these gates at least is a step towards showing that this is something that needs to be explored further. Okay, so very quickly, what is S3? The symmetries of a triangle. Okay, those there are rotations by 2 pi over 3, and there is reflection, Z2 kind of elements. And it has 6 elements in all. You can think of it as a qubit and a qubit together. Those are going to be the, on every one of these midpoints of the bonds, there's going to be a 6-dimensional Hilbert space, qubit and a qubit. And we're going to define this quantum double by requiring that these stabilizers, these products of operators, involves both the qubit and the qubit. We want all of those projectors, rather, to be 1. Okay, and won't go through the details, but we created the state on a on this small lattice, 3 by 3 lattice. So it has 18 of these sites. It's like 54 qubits. And we go and measure the projectors, and they're all pretty close to 1. If they're all exactly 1, you've exactly gotten the the S3 state. This is something less than ideal, but still pretty good enough for our purposes. Yeah, and one of the nice things you can do here is you can create a single non-abelian anyon on this torus. We always think of anyons as coming in pairs, but once you have non-abelian topological order, that's not true anymore. You can have a single excitation on the torus. This happens even for Majorana fermions, for Ising. Here you can create not just an anyon, there's actually a non-abelian anyon on the torus. Yeah, and when you go and examine the projectors, there's just one that's defective. That's telling you that you have this single excitation on the torus. Yeah, and finally we can execute these gates. So the qubits, or rather the qubit, is going to be a pair of these fluxes. So in the quantum double, you have conjugacy classes of the group as being anyons. So they are these, you're going to take a pair of them that fuse to the vacuum, at least in terms of flux, they're the same as the vacuum. And then you can have a charge that is delocalized across them, either the trivial or the so-called 2 charge, the 2-dimensional charge. And with this definition of qubit, if you're able to execute these gates, something called the pull-through, which is like Control Z, and able to measure in the Z and X bases, you can show that this is universal for quantum computing. Okay, and that's really what we did. I won't go into the details, but it looks something like this. Okay, pull-through is you take one of these anyons around one of those, that pair, that's your qubit, and it executes this particular gate on the qubits. Okay, and that's what they actually did in the quantum platform. Okay, so I'm almost out of time. I have 2 more slides. I have this summary slide and then one more to give you a little bit of a roadmap to the other talks. So in the summary slide, this is really some of the open questions. Can we keep the state cold? Can we do error correction? And that would be really helpful, of course, required if you want to do quantum computation with it. And the question is whether these toy models can inform solid state versions of this. So this S3 is actually related to SU2 level 4. SU2 level 4 is part of some read-resized states. It's also the superconductor I talked about. If you were to gauge the U1 symmetry, you end up getting SU2 level 4. Okay, so there are all these connections. Maybe ideas over here can be connected to things in solid state realizations. And about these superconductors and topological phases, we're going to hear much more in Senthil's talk. Okay, and I'm completely out of time, but let me just end with this particular slide. I just wanted to give an idea what the other talks are going to be like in this program. So we're going to hear about lattice anomalies and how to gauge symmetries, clarifying these subtle questions in Natty and Shuang's talks. Yeah, sorry, this is Shao again. And then we're going to hear from Michael and Shea about probing topological phases using two different approaches, using entanglement and putting them on exotic manifolds like the Klein bottle. Okay, then we're going to hear from Mike, maybe not then, this is not really in chronological order, about generalizing the remote detectability principle and using that to classify fractons. And finally, I'm looking forward to Dogus's talk tomorrow. So Dogus is with Periodic Labs, a very exciting new startup. And they are really trying to combine experiments and theory and large language models to discover new quantum materials. So we'll hear about that, really what's going to happen, exciting developments in the future. Okay, let me end over here.